Welcome to my third attempt to record this lecture. The first two did not save on the computer. So this is the first of the recorded lectures for the ninth week of physical geology. In this first lecture, we're going to look at streams, and then the second lecture, we will look at shorelines and coasts. So the water that we are looking at is old. So we've had oceans since the Precambrian times, and that same water is what we are using today. So we are recycling water. So when we're pulling water out of the ground, as we talked about during the live lecture, we're pulling very old water out. So water is just moving from one reservoir to another. So this is the system, the cycle, that we are moving water from one location to another. As we do that, we are altering the ground surface. So water is carving out the surface of our planet as it moves through its own sphere, its own cycle. So we are looking at streams and rivers. These are part of the surface water. So they are a small part of the fresh water on the planet. The other part of surface freshwater would be the lakes, which is also very small. So surface water is less than 1% of all freshwater. So a stream has a very dynamic system. It changes from its start to its finish, and each stream is unique. So we have different inputs and different outputs. So streams can have inputs from meltwater, from ice pack melting. They can have inputs from springs. They can have inputs from groundwater throughout the entire base of the stream. Inputs from runoff, from water that's fallen on the ground that's then drained into the system, from smaller streams, from tributaries. And then they also have different outputs. So the outputs can be loss to groundwater, can be a local base level, so where it falls into a lake that then it leaves the lake at another time. Also wetlands, or the final ultimate base level, which is where it will deposit. So true or false, all streams behave the same. This is definitely false. Each stream is a unique environment. So let's examine that environment a little bit. So each stream is going to form from a drainage network. So this is where we have the water moving across the surface of the ground, and how it moves across that ground surface is going to depend on what the underlying geology is. So the water is going to take advantage of areas of weakness and start to concentrate there, and then start to downcut. And as it downcuts through those areas of weakness, it would develop into a channel. So we see here that there's this area of darker material that is now developing into this stream, and starts to form a channel. And then as we continue, this channel gets deeper. And so this is how a stream develops over time. There are different ways they can develop. So we can have what's known as a dendritic pattern. So these often form in areas with variable geology. So the dendritic pattern will reflect the underlying geology. It's one of the more common drainage patterns. So it ends up being this very tree-like pattern that has smaller tributaries coming into larger tributaries, coming into larger tributaries, finally coming into a main trunk stream. So that's what we see here. And again, this is one of the more common patterns. You can also look at an overall drainage basin that they typically, if you look at the full drainage watershed basin, and we'll see a few of those in a bit, they have a dendritic pattern overall. We can also have what's known as radial. This happens when we have a central area of uplift where all of the drainages start and then they move out in all directions. So this happens a lot on volcanoes or things like mesas. We can have a rectangular pattern. So this is going to happen when the drainage is taking advantage of underlying geology that is in very linear patterns. So this tends to be from jointing. So the joints produce weakness in the rock. The water will flow into that weakness, excuse me, and then carve them deeper and wider. And we will see that this pattern will be repeated. So again, this normally happens when we have drainages over geology. The underlying geology has this network of joints. We can have a trellis network. So the trellis happens when we have a area where we have alternating resistant and weak rocks, and there's been deformation. So we have weak areas surrounded by resistant layers. And so we will end up having a main trunk stream that will flow across the entire area. That's what this is. And in those areas of weak material between the two resistant layers, we will develop tributary streams, and those will flow into the trunk stream independently of the tributaries in the next area of weakness. And so this overall pattern looks like a trellis. We can also have what's known as parallel. So this forms when we have steep gradients and that we have simultaneously forming drainages that run parallel to each other and that they are separated by resistant rock. So it would be too energy intensive for these drainages to cut through these divides, and so they continue to run parallel until they reach a flat area, at which point they might join up to form a single trunk. So I mentioned the word divide. So where we have multiple drainages that are separated from each other, that are independent, they will be separated by what's known as a drainage divide. This can be on a small scale. So each of these is a small scale divide. They can be on a large scale. When they're on a large scale, they're called continental divides. So these split major drainage systems or watersheds, which is another word for drainage system, apart from one another. And so they typically are separating out the overall drainage system from ultimate base levels. So in the western US, we call it the Continental Divide, that runs through the Rocky Mountains, and it splits the western drainage basin that ultimately goes to the Pacific Ocean from the Mississippi drainage basin, which will drain out into the Gulf of Mexico. If we look at these watersheds, so this map is showing watersheds from North America, and these are the large scale watersheds. And so each of these has one or two major drainage streams. If we look at the Midwestern one, all of these major rivers flow into the Mississippi River, which ultimately is what goes into the Gulf of Mexico. If we look at these in detail, we will actually see that superimposed on these larger drainage systems are many, many smaller drainage systems. So if we look at, for example, the Amazon watershed, which happens to be the largest watershed in the world. The Amazon is the second longest river, but it's the largest watershed. It is collecting water from this entire region. And so we see a very dendritic pattern. We see many, many smaller drainage basins, which are feeding into larger drainage basins, which are feeding into larger drainage basins. And so they all add up together and ultimately join into the Amazon River to then empty into the Atlantic Ocean. So this is what a watershed really is. And watersheds are made up of many, many rivers. And there are different types of rivers. So most people think of what's known as a permanent stream. So a permanent stream is a stream that is always there. It always has water. It always has water because it intersects the water table. So it is actually getting, one of its sources is groundwater. And so there's always water available. The other type of stream is called an ephemeral stream. So an ephemeral stream is disconnected from the water table. So the only water that it has access to is either runoff or if the water table level changes. So these are often called dry washes. They tend to be in more arid environments, and they can be a desert feature as well. So for a quick little review, stream channels form as they downcut and erode away the material that is beneath them, that they form as they move as water moves across the land. And so they can get this water from various places from runoff, which would be the sheet wash. They can also get water sources from groundwater, springs, melting snow, ice. So there are many inputs to streams. And these streams can form many different drainage networks. And these drainage networks come together into an overall watershed that ultimately will go to ultimate base level. This tends to be ocean or sea, or possibly a lake. And these form a variety of patterns depending on the underlying geometry. And then we have two different types of streams. We have permanent streams and then ephemeral streams. And that depends on whether or not there's water available all the time or only during certain periods. So our second embedded question. All water flows the same in channels. This is a bit of a tricky question. So basically, does water always flow the same in all channels? True or false? So the answer to this one is false. Water behaves very erratically at times. It flows the way it wants to. Even in the same channel, we can have different types of flow. So if we look at a channel, we will see that the water flows differently depending on what part of the channel we're at. So in this, we're looking at a single channel. Sometimes streams have more than one channel actually. So we're looking at a single channel here. So in a single channel, if we look at a straight section of that channel, the fastest water will be in the middle. So that's in the middle vertically as well as horizontally because we get drag along the edges. So the middle is the part where we're not having any drag. And that what's middle will spread if you have a wider stream base, but it's still, the middle is going to be the fastest. Now, if that stream isn't perfectly straight, we do have areas where we have faster and slower, and that will not be directly in the middle. So if we have curves to our stream, the fastest water will be on the outside of the curve, and the slowest water will be on the inside of the curve. So that means that the fastest water, which has the most energy, it's going to start eroding away. So we will erode away the outside bit, and we will deposit when we have slower water, so that means we deposit on the inside. So this depositing area is called a point bar. The eroding area is called a cut bank. And this happens wherever our stream channel curves. We also have different types of flow within the stream itself. So we have laminar flow, which is the straight flow. We have turbulent flow, which is the flow that is jerky and erratic, and that's going to be along the base of the bed. So it's where it's encountering obstacles in the base of the bed. So the smoother the base of the bed, the less erratic or the less turbulent flow we have. The rougher the base of the bed, the more turbulent flow we have. We can also have unusual flows in current. These are called eddies. These eddies can actually curve all the way around and become a whirlpool. So the flow within a stream is quite complicated, and so that can make measuring it rather complicated. So we tend to try to take an average, and it still can be difficult to take an average of the flow of a stream. So we care about the flow of a stream because that determines what the discharge is, what the volume or what the amount of water that we have going through. So we're going to determine discharge by the geometry of the stream as well as the speed of the water. So that means we have to measure the stream, both its depth as well as its width, as well as how fast the water is coming. So that means we need to make several measurements and get an average flow. So we're going to take this because the discharge is measured as a volume per time. So it's the volume of water per unit time passing through a cross-section of a stream. So we need to know what the cross-sectional area of the stream is, so that's the width times the depth. And we also need to know what the velocity of the water is. So that's where getting an average velocity is important. And if we multiply the cross-sectional area by the velocity, that gives us our discharge in volume per time. The discharge of the Amazon River is 200,000 meters cubed per second. So massive amounts of water moving through that river. The water available in the river will determine how much sediment it can move and carry. So the material being moved is called the sediment load. The sediment load is broken into three different types. We have bed load. Bed load is the stuff that is bouncing along the bed of the stream. It is moving through a process called saltation. So it's similar to the way that you move sediment through wind. That's basically just bouncing along. This is the bigger stuff, the larger stuff, the larger sediments. We also have suspended load. So suspended load is this fine-grained stuff that's up in the water column. So this is why when you see a large stream, it looks dirty. It's because it's carrying a bunch of sediment in it. When we get to the end of this lecture, we will talk about floods, and you will see some images of floods, and the water's all very dirty looking. It's from the sediment that's being suspended. And the final type is dissolved load. So dissolved load is the material has actually been broken down into its component ions. So it is no longer even grains. It is now back to its elements, its atoms. So this is, we can carry different amounts of material in these different types of loads. And depending on the flow character, we may carry more or less. So during a flood, we can move much more bed load than we can in regular flow. So we define these amounts that the stream is able to move with a couple of terms. So the competence of a stream is the maximum particle size it can move. So how big of sediment can it move? The faster the stream, the larger particles it can move. The capacity of a stream is the total quantity of sediment it can carry. So this is how much can it move with it. So the more volume of water, the greater the discharge, the greater the capacity. So a fast moving small stream can move large grains, but it's not going to be able to carry very many of them. But a large stream will be able to carry a lot of sediment. So the capacity and competency of a stream are related to the velocity. So because the velocity determines the energy of the stream. Once the velocity drops, the competence is going to drop as well as the capacity. So when we lose velocity, everything falls out. So we're going to drop out the larger particles first because that's the stuff that's heaviest. So it needs the most energy. So the first thing we drop is going to be the more coarse grained, and the finer grained stuff will be able to be carried further out. So we have sorting that actually occurs as we have deposition occurring with streams. So next embedded question, what load will be deposited first? Bed load, dissolved load, or suspended load? And bed load will be deposited first because it is the coarse-grained, heavier material that needs more energy to move. So stream discharge is a measure of the volume of water passing through a stream at a given time. And so it is going to depend on the amount of area that a stream is able to gather water from, so that's the size of the watershed, as well as the amount of water available, which will be dependent on climate. Velocity is going to determine how the water flows, and it is very variable, so it's difficult to calculate velocity. And that velocity is important because it's going to determine the competence, which is how well a stream can carry sediment, what size sediment it can carry. And so when we lose velocity, the sediment is going to settle out, and that will settle out based on size. So we'll actually get sorting as we lose velocity. Okay, let's look at the river system as a system rather. So we can divide the river into different zones. So we have zone 1. This is known as the zone of production. So this is the producing water and sediment. This is also called the zone of erosion. So this is the upper reaches of the river. This is often a braided pattern. I will show you a braided pattern in a second. This is dendritic in most cases. So we have many tributaries that are coming down to several main streams that will then come down into one ultimate mainstream. Again, this is where we're cutting down. We have steeper gradients, much more energy, so we're cutting down, we're eroding, so we're generating our sediment. Zone 2 is where we've moved to a lower gradient, and this is where we've moved down into a more meandering pattern. I will show you meandering pattern in a second as well. So this is where we're transporting both the water that we collected in Zone 1 as well as the sediment we generated in Zone 1. This is where we have a broad valley and a floodplain. So we're moving greater volumes of water and sediment, but we're moving them in a gentler pattern, shall we say. And then the final zone is Zone 3. So we've moved out of the zone of transport to the zone of deposition. Zone 3 is where we have a very low gradient, which slows down our velocity significantly. As we slow down our velocity, we no longer have the competence, and so we deposit all of our load. And so we'll do this either as a delta or an alluvial fan, depending on where ultimate base level is. And then the stream that's the end of the stream. So we will get back to this a little bit more, but I wanted to quickly show you what I mean by braided versus meandering. So braided streams are where we have many channels interweaving with one another because we have significant amount of sediment, and it's a very wide, not very deep channel. And so it's sediment choked. It has so much sediment and the sediment is very coarse. So we have a bunch of sand and gravel bars that we have individual channels moving between. The other type of stream is a meandering stream. So this is where we have this occurs in the lower gradients, and we have a single channel that weaves back and forth in a sinuous pattern. And so we will talk about these more a little bit later, but I wanted to make sure that I introduced those two terms early on in this process. So throughout the stream changes as we go from its start to its end. And so we start off in the source, the headwaters, the upper reaches of the stream. This is where we have a very steep profile, a steep gradient. So we have significant changes in elevation over small changes in distance. And so we have a lot more energy available here. So this is where we are generating a lot of sediment. We are cutting down. We're eroding away. So we're cutting down into bedrock here. So if we look at the individual streams, we tend to have, this is where we're collecting our water, we're collecting our sediment. So we have lots of tributaries going down. We're starting to form our trunk stream. And our tributaries are cutting down into the bedrock. We'll talk about the shape that they will develop in a second, which will depend on the bedrock. But we're down cutting in this area. And so our streams are narrower. They have less water in them because they haven't collected all the water yet. And they have a lot of energy to cut down. If we move a little bit further, we will see that these start to come together, that we're starting to form a single trunk stream. So we have more water available. We still have energy at this point, so we're still cutting down. As we move into this section, this is showing us actually that there is a local base level here that's evening out a little bit. But as we move from these tributaries to a single trunk stream, that's when we are moving out of the Zone 1 into Zone 2. So in Zone 2, we've moved into this meandering pattern. We have a single floodplain that our stream, we have a single trunk stream as well. It's going to meander back and forth. Now our stream has a much broader profile, that we have a single channel within a floodplain, and we have a lot of water. You can imagine that we have the water from this entire watershed available as it's coming down, and then it leaves the zone of transport to move into the zone of deposition, and then we're at the mouth of the stream where we've lost all of our energy because we've hit base level. ultimate base level at this point, and so everything deposits out. So first, let's look at how will our stream erode away material in the upper reaches. So we can erode away material as valleys. This will happen if we have weak material, easily eroded material. So basically we start to cut down, and then as we start cutting down into this material, it'll start sliding, slumping. We'll learn a little bit more about that next week, but it basically will start to roll down into the stream, and then we'll make this gradual slope. And so this is a valley. So this is what it looks like in real life. These are these V-shaped valleys, which we learned last week. The glaciers can take advantage of these valleys and broaden them out into U-shaped valleys. But this is because we're going through easily removed material. But what if the material is not easily removed? Well, that's the case where we get canyons. So if we have resistant material, if we have hard material, then it's not going to fall down as much. And so the stream is going to have to take advantage of weaknesses in this material. So if there are pre-existing joints in the material, the stream will cut down into those. The sides of the cut down area will be vertical, and so we will form canyons. If in doing this cutting down, the stream encounters an area of weak rock, it will actually be able to erode away more of that rock. So we can actually have undercutting. So we can have overhangs of the resistant rock and then further erosion of the weaker rock. And so you can actually see this where you'll have straight vertical rock walls that then broaden out for a short period of time. If we have an intermix of strong rock and weak rock, then we will develop what's known as a stair-step canyon. So we'll have sections of very vertical cliff face with sections of sloping cliffs that are produced by the weak rock. So the strong resistant rock will form straight cliffs, and then the weaker, more easily eroded rock will form these gradual slopes. And so we call this a stair-step canyon. We can also have changes in deposition and erosion patterns if we have changes in the base level. So if the stream changes its amount of energy, it will move from an erosional pattern to a depositional pattern, and it can move back and forth. So what can happen is that we have our original stream, it's down cutting, it's eroding. If suddenly we have a decrease in discharge, or if we have a rise in base level, well, that is going to make our stream start to fill up with sediments, with alluvium. If we then have, and so that's what we've seen here, is that these are the sediments that have been deposited. If we either then have discharge increasing, that we now have the energy to erode again, or if base level drops so that we have that changing gradient so we can erode again, then we'll start eroding into our previous deposited material. If we do that, we can actually develop what's known as a terrace. So this is where we've basically got a localized floodplain that we're cutting into this prior stream deposits. So we've got our stream channel that is then working its way back and forth across, and if it doesn't have enough energy to fully erode away all of the prior deposition materials, it'll leave a shelf, a terrace. And we can actually see this happening in multiple stages. It can go in both directions. Embedded question, true or false? The two main types of stream channels are meandering and braided channels. So this is true. We have braided channels and meandering channels. So we either have many channels intertwining with each other, or we have a single channel. So again, the braided channels, these are streams where we have excessive amounts of coarse sediment. So flow is forced around these sediment obstructions. And so we end up getting diverging and converging channels that will create sand and gravel bars in between them. This tends to happen in zone 1. This is where we have steeper gradients and very large amounts of bed load. So we are moving larger, coarser sediments. As we move down the stream system, we'll move into the meandering patterns. So these are where we have a single channel, and it will form looping sinuous meanders. So this is the curvy, loopy, snake-like streams. These tend to happen in the lower gradient areas, so they happen in zone 2. So these evolve a lot over time. So we have our main channel, and it actually originally would have flowed around here, but eventually the stream was able to cut through and make a shortcut and conserve energy by cutting off this meander. So these move both laterally, so they move back and forth across the floodplain, but they also move downstream. So our meanders, we have the fastest part of the flow is on these outer banks, so we're cutting away the outer banks, and so this meander will move in that direction. And then the slowest part of the flow is on the inside, so this is our point bar, so we're actually depositing. So the meanders will move in the direction of the cut bank, continuously depositing, and meanders go back and forth. So that means that the fastest flow is flipping back and forth. So meanders tend to make the meander neck get closer and closer together. And at some point, this bit is the this is the fast bit, and so this is the faster bit over here. Eventually it will cut through, that they will get close enough that we will cut off these meanders. And so we will develop what's known as an oxbow lake, which is an abandoned meander. If it fills in, it becomes a meander scar. So these things progress side to side, and they also progress downstream. And so, these can get pretty extreme. I'll show you a photo of a very extreme meandering stream in a bit. We can see this also in the channel deposits. We can see these point bars in the channel deposits, and we can also see the streams moving back and forth. In the floodplain, which is the area where we have overbank flow when we have floods, we also typically have what's known as a Yazoo stream that is flowing along the edges of the floodplain. So here's what this actually looks like. We have our Yazoo streams flowing along the edges. We have the main channel is outlined by trees. And then we see a lot of farming in this floodplain, because when we have that overbank flow, which is forming the floodplain, it loses all of its velocity because it's spread out over a large area, which forces it to drop its sediment load. When it does that, when it drops the suspended load, it leaves very fertile land behind, which makes it really good for farmland. So people tend to farm on floodplains. So this is showing a progression of meanders. So I encourage you to watch the meanders up here. We will see one develop and then move downstream. So this is looking at maps and aerial photos starting in 1939 and all the way through 1996. So we can see we started a meander here. There's going to be a very strong meander that will show up in this area and move downstream. So we can see a meander starting to build out here, and then it's broadening out. Now we see it moving downstream. So we see that these things migrate both out and down. And so we see it moving downstream here. So we can see it completely flipped, that our meanders went one way to the other. So meanders evolve a lot. They progress. So we erode away where we have the faster material, and we deposit where we have the slower water. So we form the point bars where we have that slow water, and we cut away. And this is what forms the meanders. And the further this process is, the more extreme these meanders can get. And eventually it gets to the point where this is the fast flow. This is the cut bank. This is the cut bank. So we have fast flow here. Eventually it'll cut through. and then we leave an oxbow lake, which can get filled in. So if you've ever been on a small stream, like canoeing or something, you may have observed this. So the fastest flow is on the outside of the point bars. That's also where you tend to see material being cut away at the base. And you also see a lot of debris falling into the rivers at this point because the support is being cut away. The point bars is where you see the slowest water, and it's also the shallowest water. And so if you're in a canoe, the stream is trying to push you into the cut banks because that's where the fastest water is. So erosion is happening where we have the high velocity flow. And is cutting away the cut bank, and this can collapse into the channel. It can also collapse higher material if you have vegetation and whatnot above it. The slower velocity is allowing deposition, so we're depositing into the stream at our point bars. So this is an example of a very active meandering system. So we can see we can see several oxbow lakes. We can see some meander scars that have been filled in oxbow lakes. We can also see a few sections where the meanders are about to cut through. So here we can see that this meander is about to cut through. This is an abandoned oxbow lake. Here we have a fairly freshly formed oxbow lake. This is an oxbow lake that's almost completely filled in. Here we have a set of meanders that was cut off. Here's another area where we're getting ready to cut through. So this is a very active system, and so this is moving downstream as well as back and forth across this floodplain. Whenever we have flooding, this also helps this process because we've cut away additional we erode away additional material. So when we get out of that zone 2, when we hit the mouth of the river, the mouth of the stream, we have to deposit. So if we do this into open land, it's going to be an alluvial fan. We tend to see this coming out of mountainous regions onto plains. So this is a pile of sediment that is depositing because the stream has hit open area, and so its velocity has dropped. So it drops out the coarsest material at the mouth, and then it gets finer and finer grained as it moves on. This will form a distributary network. So distributary is the opposite of tributary, that we have one stream going into many streams. And it will, basically what happens is that if this is the active distributary, all of our coarse stuff is piling up here. And eventually it will pile up so much that it then has to move to a different area. And then it'll pile up there, and then it'll move to a different area. So it moves back and forth, creating this fan shape, this conical shape. And it's coarse grained at the mouth because that's where the velocity drop first happens, and it gets finer and finer grained as you move out. This same process happens if the stream goes into water, but then it's called a delta. So we can have a fan-shaped delta, which is similar to what we have in the Nile River. We can also have what's known as a birdfoot delta. So that's what we have in Mississippi for the Mississippi River. So the birdfoot delta is where we have a single stream main channel that then breaks off into fewer distributary channels. And each distributary channel tends to have its own distributaries. So we have our main Mississippi River going down, it breaks into a couple of distributaries, and then the current one where most of the sediment is going down has its own distributaries as well. This type of a delta evolves similar to a fan that wants to go back and forth. It takes longer to do. So we develop what are known as lobes. So we'll have the active lobe, but we can also see the abandoned lobes in depositional deposits. And the Mississippi River is a controversial one because there are structural controls that are preventing it from moving from the current course so that New Orleans isn't abandoned. So basically the river wants to jump deltas to jump to a new location so that it can have a steeper course and and a shorter path to base level. And right now that's not being allowed to happen. And so if we look at this, we can actually see that, this A lobe is the one from, 7,000 years ago. And then it moved over to the B lobe 5,000 years ago, and then jumped all the way over to C lobe, and then it jumped back to D lobe, and E lobe is the current one, and then F lobe is one that it tried to is a subsequent one. We also have problems with the Atchafalaya River. This is an entire issue. The Mississippi River Delta has a lot of problems. So a river system is very complex, very dynamic. So it changes as we go from the headwaters to the mouth. So in the upper reaches and the headwaters, this is where we're collecting water in the watershed. We're collecting sediment as well. We're eroding away. We're cutting down into valleys and canyons. This is where we're going to have more of the braided system. As we move down stream, we have lessening gradients. We can move even into local base levels where it pauses for a moment. But as we continue to lower our gradients, we go from braided channels to more of a meandering channel. When we move into the meandering channels, that's where we're moving into more of a floodplain network. We still have lower gradients. This is where we're just transporting most everything. We do have local zones of erosion and deposition though. And then ultimately this material makes it down to ultimate base level. This is where we move into zone 3. This is the distributary network. This is where we are depositing our material. How much material is moved? The competency is going to depend on the velocity. The velocity very much depends on the amount of water available as well as the gradient. So the streams are very dynamic systems. No two streams are alike. So erosion and deposition, they give us very distinct landforms, and it's very distinct depending on what part of the stream we're looking at. They have a steep regional gradient in their headwaters, and where they're carving out canyons and valleys. This will gradually level out as they move to lesser gradients into the floodplains, and that will move into a more meandering pattern. So in the upper headwaters, the streams are choked with sediment. They are braided streams. When they move into the lower gradients, they move into a more meandering system. And then when they hit ultimate base level, that's when they start to deposit into alluvial fans or deltas. All right, the next bit, let's talk about how we can form some of our more dramatic landscapes. So what happens to the stream as we change elevation? So if we look at how base level changes with time, we start off with a stream, we have a system. If we have uplift, then that means that we're going to start down cutting. As we start down cutting, we will start forming valleys. Assuming that we can just continue to down cut and drain out this area and we don't have changes in base level, we will continue cutting these valleys, and these valleys will get less and less, and eventually we will broaden out the individual valleys. And if we keep cutting down and draining out this area, eventually these valleys will completely go away. That we won't even have this tributary network into a mainstream, that we will develop this down into a level area, and we will have a single meandering stream that no longer has a few tributaries still, but it's basically, we've moved from a upper reaches of a stream to the middle reaches of a stream just by erosion. We can also do this with evolution across the length of the stream. So if we have a stream that's already established and we have a change in base level, we can have a process called stream rejuvenation. So this means that we've already established our stream. It started it's done its erosion. It's just following its path. If base level suddenly changes through something like uplift, so that means the base level is dropped, that means that this stream is somewhat stuck in this path, but it now has all kinds of energy, so it'll start down cutting. So this is where we can get these very majestic canyons that are called incised meanders. So you can get these very strong canyon walls that are in the shape of a meandering stream. Normally you wouldn't get this. The only way you can get this is if you had a stream that was already established and then we had uplift occur. We can also have what's known as stream piracy. So this happens when you have two sets of streams that are separated by a divide, and one of the streams has more aggressive erosion. And if it erodes through the divide, it can actually capture the other stream and then force that stream to abandon its original course to join up with the more aggressive stream to move to its base level. So that can form what's known as a water gap. If we have uplift occurring with streams, we can actually have two different types of streams forming. So if we have a stream that is eroding as uplift is occurring, that's called an antecedent stream. So that means that it's eroding through the material as it's uplifting, and so we create a pass in this material. If the stream isn't able to keep up with erosion, it will actually change its pathway, its course, and won't cut through the material. The other type of stream we can have is what's known as a superimposed stream. So this happens, this is basically when we got the incised meanders. So this was a stream that had already established its path, and it's starting to downcut into the material that's already there. So this is happening that we already had this material had undergone its shaping, and then we're down cutting into that material. And so we're not seeing the strong incised meanders. We are seeing, or I'm sorry, the incised meanders are more an antecedent stream. So we're seeing that this is going to be a more simple pattern, but we're down cutting into material that was already there. So basically you can either have a stream that keeps up with erosion and cuts down as material's moving up, or you can have a stream that cuts down into material that is has already been deformed in some way, and so it's cutting across this material, but it's the stream comes last. So I want to talk about floods for the last bit. Floods, I have a particular feelings about floods. I'm originally from St. Louis, Missouri, so I've lived with floods my entire life. I experienced some significant floods. So it's something that I feel is important to talk about. Floods are also something that can happen in many, many places for many, many reasons. So we have seasonal floods, which are what I first think of with floods. So these are where you have overbank flow for a large drainage, so large rivers, and these tend to take time. They can take hours or days, that you can watch the flood stage rise. So this means that people can prepare for them. They can start sandbagging or they can evacuate. But even still, there's a lot of damage. There's massive damage. We will see that. And massive loss. So, seasonal monsoons can cause massive flooding that can cost hundreds of thousands of lives in other countries. So in 1990, there was a monsoon that killed 100,000 people in Bangladesh. The other type of flooding that we can get is flash flooding, which happens much faster and can happen anywhere. And flash flooding is very dangerous because it's not something we can anticipate. It's not something we can prepare for. So we're going to talk about both of them a little bit. So embedded question. Floods can happen anywhere there's water, true or false? So this is true, of course. So floods can happen in your house. They can happen on a river. They can happen on a beach from a storm. They can happen in a city due to a blocked storm drain. So floods can happen anywhere. How do we measure a flood? So we measure a flood using a recurrence interval. So basically we're trying to define in a given amount of time, or how many years would we expect between floods of the same size. So if a flood is if a flood is in a 10-year flood, that means we expect to see one flood of that size in a 10-year period. So the way we determine this is we have a list of floods that are ranked by size. So we need to know the frequency, how often they occur, and the size that they are. So the recurrence interval is going to be the averaged years between similarly sized floods. So what we're going to do is we are going to calculate our recurrence interval R by taking the number of years in our record and adding 1 to that, and then dividing that by the rank of flood we're interested in. So, and when we rank these, 1 is the highest. So our example data set here has 9 years. So this flood in 96 is our rank 1. So if we're trying to figure out what our recurrence interval is for our rank 1 flood, we would take our data set of 9 plus 1, so that's 10, divided by our rank, which is 1. So 10 divided by 1 is 10. So that means that in our 9-year data set, the largest flood is a 10-year flood. We should expect 1 flood of this size in a 10-year period. If we look at the middle one, so this is the flood from 95, which is a rank 5. So if we take our number of years, which is 9, plus 1, so 10, divided by our rank, which this case is 5. So that means that this flood is 10 divided by 5 is 2. So this is a 2-year flood. So we would expect a flood of this size in each 2-year period. So for that rank 10, so our 10-year flood, that means we expect 1 event of this size in every 10-year period. So in a given year, the probability of this 10-year flood is going to be 1 in 10, or 0.1, or 10%. So that means you could have 2 years with 10-year floods and then not have one for another 10 years. It's a statistic over a period of time. Now, the thing to be cautious about here is that you can't calculate this out any beyond 2 times the years of data you have in your data set. So our data set has 9, so that means we can't go beyond a 20-year flood. Even going up to that 20-year flood's a little bit sketchy. So to calculate these things accurately, you need a long data set. And it's important to calculate these things accurately because these measurements go into the risk assessments that are then going to determine building codes and where people are allowed to build buildings, where you're allowed to put your house, what's zoned as commercial versus residential. And it's not always ranked correctly, I might add. We will see that in a bit. So floods can occur anywhere. Flash floods especially can occur anywhere. So they are extremely dangerous. A flash flood is defined by a fast rise in water. That water tends to be moving quite fast and has very little warning. So a lot of times these will happen in that zone 1, those steeper areas or small tributaries, but really they can happen anywhere. So intense rainfall over a short period of time tends to trigger them, and you have more potential for a flood if the infiltration, if the water can't get into the ground, so if it's hampered in some way. This can be due to the ground's already full of water, it's fully saturated, or if something's preventing the water from getting in. So if you have a lot of pavement or if you have a lot of impermeable surfaces, then the water is going to be runoff and it's going to channel into smaller areas and overflow very quickly. So this happens commonly in arid or semi-arid environments. If you have steep topography, if you're funneling your runoff, if you have large amounts of pavement, so this is why you get urban floods, or if you have times when you've broken whatever's holding back massive amounts of water. So if you have a breach in a dam or a levee, or if you had ice jamming that has then been released. So that means that you had a buildup of water that's been released. And I will show you an analog of a dam breach in a moment. So this is pictures of the aftermath of a flash flood that occurred in Colorado in 1976. So this flash flood happened after more than 7 inches of rain fell in an hour, and the discharge in this big Thompson River was 4 times the largest recorded maximum discharge. This flood ended up killing 144 people. So they are very, very dangerous. And this is the analog of a dam breach, and then I will show you afterwards a flash flood in my neighbor's backyard. So I'm going to flip my camera up, or my microphone up, so hopefully you won't hear me. There will be closed captions built into this video. So this is a video showing a dam breach. So they have built an artificial dam, and they will breach it. So they've built this earthen artificial dam, and they are slowly trying to form a breach, and they want to measure how fast the rest of the dam is destroyed by that little breach to start. So this was a fairly small area that was breached into this earthen dam, but water's very, very powerful. So we can see that water has started flowing out. They have several cameras running, and they flip back and forth between them. But water's running out now, and this is underwater at the beginning.
Really liquefied at the bottom.
So we can see that the water is coming out. They have those beads as markers on the top. So we can see that those beads are going to start coming out faster and faster. We can also see that this has gotten wider. It's going to get wider and wider and wider. We're also cutting down here. So we can see things are starting to move much faster.
I might shoot the toe here. It's starting to really.
And we also have a wider area here at the top. You can see it's down cut quite a bit as well.
Oh my. Yeah, it's turning into she's gonna make it.
Yeah, you're just in time. It's just starting to break.
Everybody, please remember that there are cameras
right there, so
you can stand behind the ladder. Yeah, behind the ladder is fine.
Okay, thanks. So you can see the water's coming out faster and faster and faster. And now we can see that we're starting to have collapse within as well. So we're starting to break out some of the bottom now. So you can imagine how catastrophic it is when a dam fails. And there have been major flood events due to dam collapses, and now it's gone.
Okay, you can quit, Chris.
Yeah, and there was a big chunk of the side just went. Water is very, very powerful. So you can imagine just how much damage this would be if you scale this up. If you had a full-size dam for a lake that failed like this. There have been full-size dams that have failed like this. There were cases, there was a famous case a few years ago in Missouri where one of the power company's dams failed and completely destroyed an entire region. I believe the only people that lost their lives were the people that were in charge of the dam, or that were monitoring it. And there's still more water coming. They've basically destroyed the entire dam, and there's more water still to come. And there's no way to stop this. When this starts, there's no way that someone could come and stop this. This is, you can't sandbag this. This is something that once it starts, that's it.
this will be the same one thing I threw that episode of earlier was like, one here. More material. But yeah, overall, makes sense. Also switch off the wrong. Yeah.
So an example of a flash flood on a much smaller scale, much faster scale as well. This is a picture out of one of the side windows of my house. My neighbor has a drainage that goes through his property, and he has a little bridge over it. His bridge had to be rebuilt. This is the rebuilt bridge. This is a video.
So here is the drainage from out the addition window. This is insane. Oh my god, I can't believe this. This is crazy. That's so much water.
I apologize for my
Wow.
recording.
This is out the kitchen window. This is insane. Look at that. Jeez.
And my dogs were looking at me like I was crazy too. I apologize for my voice during the recording. Normally when I'm teaching this class, I can mute that. So I will say that I'm pretty sure when I took that video, the bridge was not actually there. So I don't think it's above the bridge at this point. This happens routinely in the property next to my backyard. This is because the drainage system just gets overwhelmed and it just fills up this area, and then it's normally gone within a few hours. So that is a flash flood, an urban flash flood. So floods happen wherever you have water. And how bad a flood is going to depend on how close you are, what type of drainage it is, etc. So these risks are determined by ranking those floods and determining what rank of flood they are, and then what probability that flood has. And so that determines what type of insurance is necessary, where people are allowed to build, what they're allowed to build, etc. If those maps, those hazard maps, are inaccurate, this can lead to very hazardous conditions where you have massive flooding and lots of damage. Water causes lots and lots of damage. So one way to try to reduce this is to have designated floodways. So these are areas where we don't allow people to build. This gets challenging in major cities. Many major cities are near rivers, and so you have issues that people are, there's a limited land, so people don't want to leave it unbuilt up. So there are different ways to try to control some of these. Controlling rivers is very challenging, and so by trying to limit where people are allowed to build, this is a way to try to reduce the damage from floods, to keep people and structures safe. It does not always work. Water will find a way. So the next video is looking at case study for Mississippi River flooding. I will again flip my mic up. There's closed captioning in this video that is already built into play. So here's a case study of the Mississippi River. The textbook I was using only did it through 2008. This continues, and I believe I have a couple of videos showing this. So 1973 was a 100-year flood. There were a few deaths, about $1.2 billion in property damage. It was minor compared to what we would see in 1993 and 2008. The Great Flood of 1993, the flood of 93. I was there for this. I remember this distinctly. It was much greater than 1973. It occurred all summer. This was flooding on both the Mississippi River and the Missouri River. So the Missouri River enters the Mississippi River at St. Louis. So there was massive flooding in the entire area, and the floodwaters didn't recede all summer. There were about 50 people died and $15 billion in damage. There was major flooding in 2008, mostly in June. About 24 people died and $9 billion of damage. We're talking $1 billion of damage. So these are all 100-year floods. 3 100-year floods in the past 45 years. Begs the question, are these actually 100-year floods? See if this actually comes up. So this is the Wikipedia page for Mississippi River flooding. 1543, that would be via historical documents and landform evidence. 1734, 1788, 1809, 1825, 1844, 1851, yada yada yada. Let's go to the more recent ones. So 73, 75, 79, 83, 93, 2002, 2008, 2011, 2014, 2017, 2019. These are not 100-year floods. So we have these are called great floods. This is what I was talking about when I was saying that sometimes floods are mislabeled, that they're labeled as being a 100-year flood when they occur much more frequently, and this can cause problems with zoning and let people think that they're safe when they're not. So yeah, there have been many floods. So 2019, the Mississippi River was flooding similar to 1993. 2017, historical flooding, record flooding. So these are not just isolated events. All right, this video is from 1993. It was put out by one of the local news agencies. I remember watching these events on TV live as a kid. You want to play?
There had been some spring flooding along the Missouri and Mississippi, but that happened every few years. A couple of feet of river water on a few low-lying areas. The spring of '93 was nothing special.
But miles upriver in Des Moines, Davenport, Dubuque, all along the upper Mississippi, the spring rains continued falling and the rivers began rising. A wet spring would evolve into a record-breaking summer.
First it was an annoyance, then it became a major disaster, but new predictions put the Mississippi flood crest at 45.5 feet in St. Louis.
Our top story tonight at 10, a call is out tonight for more sandbaggers in South St. Louis.
The city's fire chief sounded the call after seeing what you just saw, a new higher forecast for the Mississippi.
Hundreds of families now face the very real possibility of losing their homes.
The true impact of the levee break wouldn't be known until sunrise, Saturday morning, July 31st. As St. Louisans awoke to Today in St. Louis, anchors Jeff Fowler and Gene Jackson showed the city and the nation some of the most incredible pictures we're ever likely to see.
The Monarch levee broke at about 10:30 last night, sending water spilling into an area of Chesterfield. It has flooded many farms. It has covered Highway 40 from just west of Clarkson all the way to Highway 94 in St. Charles. We are told in some places that
I just have to break in here. So the smokehouse still exists, And now there is a strip mall as far as the eye can see along the highway that is currently underwater in this video. And it's a very, very built up strip mall. I watched it being built up throughout. This is the road we would take to drive from my parents' house to where we went to university. And every time we went back and forth, we would see more and more buildup. This was all, at this time, there wasn't very much out here. There were ball fields, the smokehouse, and then there was a pumpkin farm. Now there's a jail, there's car dealerships, there's a strip mall. There's still ball fields, but this guy's still there.
Water is 4 to 5 feet deep along Highway 40. My partner Gene Jackson is in Chopper 5 with Alan Barklage at this hour, and they're over Highway 40. If you can see it, Gene, good morning.
Jeff, that's the trick. Can you see it? It's tree line, and the water is almost up to the tops of the trees here in Chesterfield Valley. And this is in an area where there's not supposed to be water. So you can imagine the damage that's being done. And Jeff, the debris is just horrendous. There's floating crates, barrels with who knows what's in them. Cars, you name it.
Gene, we can see we just saw at the top of the screen the Daniel Boone Bridge there. That gives people a pretty good perspective on the area we're talking about. And yeah. I mean, it's just, there's just no way to get near that bridge.
No way. In fact, the entire section of Highway 40 is closed in both directions from the Daniel Boone Bridge back to almost Chesterfield Mall to Clarkson Road.
As Saturday turned into Sunday, the attention of St. Louis and the world would turn to the bottomlands of Illinois. It would be a memorable day where the river would once again show its incredible power. The drama played out live on News Channel 5 as Jeff Fowler, Gene Jackson, and helicopter pilot Alan Barklage narrated the live pictures from Chopper 5 as it hovered over the Monroe County farm of Virgil Gummersheim.
There's an actual breach in the levee at the farmhouse, and water's just flowing through it at a tremendous rate. Now, the problem is, they could probably have another hour or so up on the levee before too big of a problem, but if that levee starts to go, there's no telling how long the levee or how large of a stretch of the levee will break at one time. The difference between the levee break earlier and now as we come around the tree here, it's unbelievable how quickly this water starts coming through.
It's digging a pretty good-sized hole, probably 5 feet deep right now in front of where that levee was.
Do you remember that video
are being washed right down in there with it. You can see it coming around the other side of the farmhouse now and filling up in front of some silos.
Water is pouring through into this area.
Yeah, it's racing in there now, Alan.
And it's getting bigger by the minute. Before too long, this is going to be a major break in the levee.
If Joe can pan over and show us the house, I think you have to wonder whether the home is going to be able to withstand the force of the water.
Here we go. Here goes a part of the shed that held and housed a lot of the animals. It's now washing away. You saw the walls collapse underneath, and the roof and the contents are now washing away in that flood water.
That house is starting to go.
Oh, Jeff, it's unbelievable. There it goes. Just now lifted off the foundation, and it's just crumbling in the rapid and the violent waters here that are coming through this levee bridge about 3 miles south of the Jefferson Barracks Bridge. We've watched the silos go, we've watched the barn go, we've watched a shed go, and now the house itself has been lifted off the foundation by these floodwaters. It's just unbelievable.
And the
trees are actually snapping in two as well. It's just a tragedy.
Alan, in relationship to what you've already shown us, maybe Joe can get a wider shot and look back the other way. How many other farms do we have there that might be?
Okay, we're gonna bring it around and we'll show you as Joe comes by. There's some farms out in the background there, and you can see that there's still farmland here, and this water just keeps heading towards the farmland as we come all the way around. There's another big farm and some of these farms there's 10, 15, 20 feet of water in the farms already.
My apologies. Gidget is crying right now, so if you can hear her, my apologies for that. All right. So I have been forced to watch that video now 3 times today. This is the 3rd time I've tried to record this lecture. I've watched it probably at least half a dozen times over the past couple days. It still gets me. I still remember watching that house being swept away by the flood waters as a little kid. thinking about it, asking my parents, are we in danger? Are we safe? My parents assuring me we live on a hill, we are safe. Everyone in our family lives on a hill. I think my parents were honestly lying to me because it didn't matter. Most of our family weren't in flood areas. I also want to point out in that video the two regions that they showed. Chesterfield, the first part they were showing, that's the Missouri River. The second part they were showing in the lowlands of, or the bottomlands of Illinois, that's the Mississippi River. Now, part of the reason why 93 was such a significant flood season was that you had flooding on both rivers. And again, St. Louis is where the Missouri enters into the Mississippi. So you had two major drainages, or one major drainage entering as a tributary into another drainage, and both were flooding. So to review the last little bits, we can have streams that are superimposed, so they have their shape and then they cut down into rock structure that already exists. Or we can have antecedent streams that cut into rock while the land is being uplifted, so they're cutting down as the uplift is occurring. And then flooding is a problem everywhere. It's a big problem. It's a natural cycle. Floodplains are floodplains because they flood. We have flooding in floodplains. We also have flooding in deltas. And then we can also have flash floods. So flash floods are the ones that are unpredictable and short-lived, but very, very dangerous as well. So next time we will talk about coastal processes.